I want to thank also the organizers for giving me the opportunity to talk here today about a topic that has occupied me for almost 20 years now. And I'm happy to share it with you, and I hope at the end you will be enthusiastic and you will want to continue in this field because there are some interesting open questions. Also, during the talk, do not hesitate to interrupt me. You see there are 101 slides, but we don't have to cover them all. But we could, I mean. No, that was not me. That was Antoine, probably. No, it depends how if every transition is counted for a page or not. So the slides are available on my web page, but they're also available on the summer school website. So this is my table of contents. I want to start with an informal introduction to the topic. I will have a brief recall on integrity constraints, although we have seen a lot of it in Andreas' talk already on Monday morning. I will talk about various repair notions, the problem of repair checking, and then the main topic will be consistent query answering conjunctive queries like CCQA. And then after the break, I want to give you some technical proof about one of our interesting results. And maybe at the end, if there's time left, we can talk about other kinds of constraints in queries. So let me start by why and what is database repairing. By the way, there is like a paper that was published in 2019 in the database principles column of Sigmod Record. And I think for all of you, I think you should have a look at this database principles column because there are really great papers on many topics of interest. So you should go there and not only read my paper, but also the other papers that are around there. And most things I will talk about today, they are available in that paper that takes about 10 pages, I think. And actually, this work on consistent query answering started at the ACM POTS conference, ACM POTS in Philadelphia in 1999, so the previous century, by a paper by Marcelo Arenas, Leo Bertossi, and Jan Chomitsky. At that time, the paper was presented by Leo Bertossi. And actually, I was present at that paper presentation. And so the title is Consistent Query Answering in Inconsistent Databases. And so at that time, it was already realized that, I mean, databases can be inconsistent. And the question is, how can we answer queries in a consistent way if the database is known to be inconsistent? And what's nice here that in the beginning of the abstract, they immediately say that they want to have a logical characterization of the notion of consistent answer. So the motivation was really like, let's try to do a logical approach. So today, when you have a inconsistent database, most people, they say, oh, let's clean the data, right? And this is like an engineering approach where you put a lot of work in cleaning the data. And like what they tried to advertise in that paper was like, okay, keep calm and try to use logic, right? And so that's what I'm trying to talk about today is how by using logic you can deal with inconsistent data. So here's a first example. I will use a lot of examples throughout this talk. Like, suppose you have a taught-by relation where you have a course, a teacher, and a semester, and then you have this functional dependency stating that every course has a unique teacher and a unique semester, right? And then you have a database where this constraint is violated because you have a computer science course and you have two different teachers. Either it's Dave Meyer or Jeffrey Ullman who's teaching this course. Confronted with this situation, you may ask, okay, what can I do about the data? And intuitively here, like you can repair it in an obvious way. You say, well, one of the two tuples has to be wrong. So I can make two repairs. Either I keep the first tuple or I keep the second tuple, right? So this means we will have two repairs, and they are equally good. Without further background information, you don't know which one you should prefer to the other. So you say, okay, we have two possible worlds, two repairs, and that's fine. I mean, I have to live with it. And then the question is, how do we answer queries if we have two or more possible worlds? And the answer given by consistent query answering is you just intersect the query answer on all repairs, right? It seems the sensible things to do. You only return answers that are true in every repair, right? So for example, if I would have the questions here, give me all courses taught in the fall semester, then you in both repairs, in the fall semester, you are teaching computer science, this course, so this will be a consistent answer to the query. But if I ask the question, give me the courses taught by Dave Meyer, then the consistent answer will be empty, because there is a repair where this course is taught by Jeffrey Ullman, and in that repair, Dave Meyer is not teaching any course, right? So that's the idea of consistent query answering. So probably this is the most important slide of this presentation. So if what we have here an inconsistent database, and then we have a set of constraints. So it's always with respect to a fixed set of integrity constraints, and we have a query lowercase q. And then we will see that there are different notions of repairing the database, but the idea is typically you end up with a number of repairs. And the number of repairs can be exponential, can even be infinite, right? But now if I have a query queue on my database, the idea is to answer this query, what I will actually compute is the intersection of the query answer over all repairs, right? And the number of repairs can be infinite, so this can be an infinite intersection, but the result will be finite, right? Because every repair is finite, and every consistent answer will be already in the answer to Q on R1. So we have a finite set of consistent answers, right? Now, what we are interested in consistent query answering is not to build all these repairs, but to find here like another query which is uppercase Q, so that if I ask uppercase Q on the inconsistent database, then I get the same result, right? So this means that if I can find this uppercase Q, and if it's tractable, polynomial time, then actually I don't have to construct any repair. I just ask uppercase Q on the inconsistent database, and I get a consistent answer, right? So that's the main idea actually of consistent query answering. And so in this talk, it will be a lot about how do we define these repairs, and what will be the complexity of computing this uppercase Q, right? Good. So here's again a very simple example. Suppose I have the same database, and I ask courses taught by Dave Meyer, and my Q, lowercase q, is just like, of course you can read this like, is there a course X? Give me all courses X that are taught by Dave Meyer. And in this case, I could give this as an exercise, like we called it yesterday, but probably you will easily see what will be the uppercase Q here. Well, the courses taught by Dave Meyer, they are certain, or they will be true in every repair. If I have a course where I only have Dave Meyer as a teacher and no one else. Well, this actually I can express in first order logic. Uppercase Q is like give me the courses taught by Dave Meyer, and moreover, and the second line is stating there should not be another tuple in my database that gives another name than Dave Meyer for this course, right? So in this case, in this situation, I mean, if I want to answer lowercase q, instead of computing the repairs, I can just take uppercase q, ask it against my inconsistent database and get the consistent answers, right? So in this case, the situation is easy. Uppercase q is just another first order query, right? But we will see that the situation is not always that easy. Now, maybe I should say a word on data cleaning and consistent query answering. So the difference I see is like data cleaning, and data cleaning, it's often expensive. It's a long process. And the idea is that before answering any query, you should first clean the database. And this may take a lot of time. And I think the advantage of consistent query answering is that you can immediately start querying the database, get consistent answers that will be true, independent of how you prepare the database later on. But of course, these answers may be incomplete. But what you get out of it, it's always an answer that is consistent, or that will be true in every repair, right? Today, often these two are presented as two extreme solutions. I think there should maybe more work on trying to combine these both approaches, but okay. Well, this has been introduced already before by Andreas in his first talk. So we have a database schema, you know what this is. We have integrity constraints. In this talk, all integrity constraints will be first order sentences. Often they are called dependencies. You have a database instance, as you have seen on Monday morning, associates a finite relation to every database relation name. But often we want to look at the database as just a set of tuples, because then we can talk about maximal subsets and so on. So that's also what we do here. So a database is basically just a set of facts. And then, okay, we can give names to attributes, or we can just use positions. But I think we have seen that before. Now, what's a consistent database? A consistent database, of course, is just a database that satisfies all constraints. And then we will define a repair as a consistent database. Repairs have to be consistent, of course, and they have to differ from the database in some minimal way. Now, what is meant here by minimal will be defined later on in a more precise way. Right? Yeah, you can also view each repair as a possible world. And that brings us to the talk of Antoine this morning. It's like, you can see it as possible worlds. And this brings us in the world of incomplete databases, where you have famous paper like the paper of Mielinski and Lipski, and also in the database textbook, Abitable Hulviano, there's a chapter 19 on incomplete databases. Right? And then the way we define a consistent answer, so if you have a first order query, lowercase q, you look all tuples with constants, should that every repair should satisfy this expression, right? So the tuple A1 to AN is a consistent answer if it's an answer on the query on every repair. And so from an incomplete database viewpoint, consistent answers are just what they call certain answers. And if you look at my old papers, the titles I often use like certain query answering, because I like this idea very much that it was just certain query answering, up to a point where one reviewer told me you should not use certain query answering, it should be consistent query answering, be consistent with the paper that introduced consistent query answering. So from that point on, I always use consistent query answering the title. Okay. Okay, when I was attending Val's talk yesterday, he was talking about this book as the Bible of database theory. And I was thinking, well, if this is the Bible, then all I've been doing in the past 20 years should be motivated by the Bible, right? So I took a look at the book, and I actually found that there is a sentence, but this is the Alice book, you know, because it's about Alice. But you see the sentence found in the introductory chapter on incomplete information. It said, partial information may also arise when we cannot completely rely on the database because of possible inconsistencies, example given, resulting from merging data from different sources. So it's in the Bible. And that's actually that's actually the main reason today that's often people often say, well, databases can become inconsistent when you merge data from different sources. Even if the sources themselves, they are all consistent, when you merge them, they can become inconsistent. So that was a relief to find that sentence. So database repairs is easily to see that they can be exponentially many. So if I take a simple relation with only two attributes, and you have like a functional dependency, A determines B, so saying that A is the key, and then I construct a relation like this, where these dashed lines, they separate what we will call blocks. So blocks are tuples with the same primary key. Then you can easily see that the number of repairs is 2 to the power n, where n is the number of blocks. And if you want to rephrase this in the number of tuples, then you get this expression. So the number of repairs can be exponential, right? Now I have to give introduce some integrity constraints, and some of these constraints, they have been already introduced. So, so first we have functional dependencies, right? They have been introduced by Andreas. I will not repeat it. So it's something like R, X determines Y, and it's satisfied by a database. Whenever you have two R facts that agree on all attributes of X, they should agree on all attributes of Y, and we call this a key dependency if the right-hand part is just sort R or all the attributes of R, right? We have seen this before. Inclusion dependency is another important dependency we have seen Monday morning, and it's like, this is the syntax, and I will not repeat it, but you see, whenever in R I have a tuple, then all these values should reoccur at given positions in the S relation. Now let's try to generalize this, like a tuple generating dependency. They have been introduced, I think, in previous talk, but let me be precise about this. So I assume here that I don't have constants, and the syntax of a TGD is this, like for all X, and then I have phi of X, it's just a conjunction, and then arrow implies there exists a Y, such that psi XY. And psi XY is also a conjunction of atoms. So you can think of phi and psi as disconjunctive queries. Right? And something that's not always said is that this psi should not be empty, so that if you have an empty database, then it satisfies every tuple generating dependency. And then there are two specializations. A tuple generating dependency without existentially quantified variable is called full. So if there's no existential quantifier here, then it's called full. later on in the talk. And a love TGD is a TGD where on the left-hand side, or the phi here, is just a single atom. I give some examples, like a full TGD. Here's an example just stating like the relation R should be transitive. Say if I have XY and YZ, then I also have XZ. This is full, and what's nice, if it's full, then it's straightforward to chase, right? We have seen the chase on Monday morning. Here chasing just means whenever the left hand is satisfied but the right hand is not, then you just add a tuple. Yeah? So actually you're computing the transitive closure of R. And it will always terminate, right? Because you'll only have a finite number of constants in your database, and you can only generate finitely many facts in this way. A non-full TGD is like this, something like every part of length 2 can be extended in a part of length 4. You have X, Y, Y, Z, a part of length 2, then there exists U, there exists W, and then you have another conjunction. Right? This is not a love because on the left-hand side I have 2 atoms. I always forget between love and gav why these are used. And in my mind, I think about love as the LA is for a lonely atom at the left. The L is for left, and A for atom, a lonely atom at the left. You know, this way you will never forget it. Actually, the truth is something like local SVU and global SVU, but I can never remember what that means. So, right? So this is not a love because there's not a lonely atom at the left, and this is a love because here you have a lonely atom at the left, right? And these things are, of course, more difficult to chase because of these existential quantifiers, which will always invent new values, right? Then universal constraints. Universal constraints have this form. It's a universal quantifier. Then you have a conjunction of atoms. Then you have the beta X is like a Boolean combination of equalities, probably sometimes also even inequalities. And then you have a disjunction here. And I guess the reason why this is called universal constraint is because it's universally quantified and there are no existential quantifiers involved. And then there are some special cases. We say that we have a denial constraint if m equals 0. So if m equals 0, you have on the right here the empty disjunction, and the empty disjunction is just false. And then we can rewrite it in this form, you know, and this is already very close to an EGD, equality generating dependency, if beta is a negation of an equality. And also often it's convenient to think about it as the negation of a conjunction of this type. So you think of it as a denial constraint, as the negation of a conjunctive query where you have some combination, some Boolean combination of built-in predicates. The point here is that if you have, and that will be important later on, if you have a database that violates a denial constraint, then adding tuples to that database will not solve the inconsistency, right? And then you have an EGD if this m equals 0 in this beta is a negation of an equality, as I stated before. This is also of the previous form. So an example of a denial constraint, and this is also an example I will be using later on. Suppose we have like this database, and we say a reasonable constraint is no clerk earns more than any boss. You can say there does not exist one first employee and a second employee, such that the first employee is a clerk, the second employee is a boss, and the clerk earns strictly.
that's denial constraint, and for this database, it's satisfied. Right? Here's an overview of all these constraints. So you have key constraints. There are functional dependencies, heavily functional dependencies, and EGD. EGD, as we have seen, is a special kind of denial constraint. This is a special kind of universal constraint. Inclusion dependencies, there are like love TGDs, which are TGDs, of course. And then we have a full TGD, which is, of course, a TGD. Yeah, the weakly acyclic, I will not introduce them here, but these are like TGDs for which the chase is known to be terminating. And then here, a full TGD is also a universal constraint, and I leave this as an easy exercise. Actually, the way you should read this diagram is like every, for example, every set of full tuple generating dependencies is equivalent to a set of GAF TGDs, if you know what's GAF TGD, right? Okay, so this is the picture, and I think Andreas told us that, or mentioned that in databases, the only most reasonable constraints are TGDs and EGDs, and yeah, I think, well, the denial constraints. Universal constraint, yeah. Yeah. This is not captured, no. Yeah, by FO, yes. Yeah, so FO is first order constraint is everything. Yeah, that there are, like, if you look at the old books of Bernard Thalheim, if you know the person, he has a book with plenty of other types of constraints. But I think these are the most used ones. So now we will talk a little bit about these different repair notions. And we will talk about tuple-based repairing and also value-based repairing. So how do we define a repair? So we on an abstract level, we can proceed in 2 steps. So for any database, I define a binary relation, which will denote like this, which depends on the database, and I will define something like R smaller than with respect to this database than S, which should capture the meaning that R is more or equally similar to the database than S. So the idea is that we want repairs to be as close as possible to the original database. And so this is captured by this. So you could also say the R is at least as close to the database than S, right? And once we have this, this binary relation, we can define repairs. So assume that you have a set of integrity constraints, and you have a database, and you say another database is a repair with respect to the database and the constraints. If the first condition simply states that every repair should satisfy all constraints, it should be consistent. And then here the second condition states that for every other database, if it's strictly closer to the database, then it should not be consistent. Right? Does that make sense? So a repair should, of course, be consistent, and it should not be possible to find another database that's strictly closer to my original database, and that's also consistent, right? Now here you have this strictly closer. It's defined as is in the footnote here, right? That's the definition of being strictly closer you could use, like.
And then, of course, maybe you should impose some properties on this relation to make repairs exist. And it's sufficient to just require that this relation be acyclic, so that you cannot have something that's closer than something else and closer than itself and so on. But as we will see, in most cases, this will define even a partial order. So but that's the idea here. Of course, I have not told you up to now how this is actually defined. So this will be this will come now, right? So this is a very important notion, and I think it's very intuitive, right? So first, tuple-based repairing. So here we are defining this notion, and this was actually the definition that can be found in the original paper, 99 paper that introduced consistent crayoncing. They use symmetric difference repairs, and they say, well, let's say that R is closer to the database than S if the symmetric difference of R with the database is included in the symmetric difference of S with the database. So the symmetric difference of a set, you know, it takes all tuples in R that are not in the database, union all the tuples in the database that are not in R. Right? You know the symmetric differences. So when you start reasoning about this expression, I find it often difficult. So I have if I'm reasoning about this, I use this expression as equivalent, saying that R is closer to S with respect to symmetric differences if these two inclusions hold. So the intersection of S in the database should be in R. So every tuple that's from S that is in the database should be in R, right? And every tuple in R should be in S union the database. So every tuple of R, if it's not in the database, then it should already be in S, right? Just equivalent. So, but I think this is easily. So it also means that in this way, R is a repair. If you delete from R any tuple that was in the database, then R will become inconsistent. And if you delete from R a tuple that was not in the database, then R will also become inconsistent. So you preserve as much as possible from the database, and then you add the minimal amount of, you do a minimal amount of insertions. And with this notion, you can easily prove, that's an exercise, that this defines actually a partial order on your databases. So that's nice. Furthermore, we say that a repair is a subset repair if it's included in the database, if it's a subset, and a superset repair is a repair that contains the database, right? And as I mentioned before, if you only have denial constraints, then for denial constraints, remember denial constraints, you can look at it as the negation of a conjunctive query. If it's falsified, then adding tuples will not solve your inconsistency. So for denial constraints, if you want to repair a denial constraint, you have to delete tuples, the tuples that together violate, of one of the tuples that contribute to a constraint violation, right? And there have been many other notions of repair. One thing you could do is, okay, instead of using this as an inclusion of sets, you can just say, what happens if I use just cardinalities? Instead of having a subset here, I just compare cardinalities, and I say I have this relation if the number of tuples I have to change to obtain R is less than the number of tuples. The number of tuples I have to change to obtain S. I will give you an example on the next slide. And in this case, this relation is not a partial order, it's a pre-order, which is, it's reflexive and transitive metric, right? That's also easy to see. Okay, so most of the results I will talk about later on is really about these symmetric difference repairs. So here's an example. Assume you have this inconsistent data. This is an inconsistent database, as we will see. So we have like every employee as a rank and a salary. And then we have this constraint stating that every clerk earns less than any boss. And here you have a violation, right? Because possible violation like here, Anne is the boss earning 20 and Anne is a clerk earning 40. And here's a problem, of course, because if Tim is a clerk and Anne is a boss earning 20, then there's a clerk earning more than the boss. So this is an inconsistency. So how can we repair this inconsistency using a symmetric difference? Well, since these are denial constraints, I know that the only way to repair the database is by deleting tuples. And now I will try to delete a minimal set of tuples with respect to set inclusion. So I have two symmetric difference repairs, the one on the left here and the one on the right, right? At the right, I just get the information that N is a boss earning 20. And then the left one, I have all clerks, right? And you can see this is a repair because if I add one more tuple, then I will have a constraint violation. Of course, also because N is a primary key. And here also I cannot add any of the clerks because all these clerks earn more than 20, right? So these are the two repairs. Of course, here you might say, well, is this the most intuitive way of repairing? Because you could also think that maybe something is messed up here. Maybe she is a boss earning 40. But the repair notion I have seen so far, it's just like you delete or insert entire tuples, and you do not look at subparts of tuples or subtuples, right? So we have to live with these two repairs. If you look at cardinality constraints, then this one is not a repair because here you have, it's obviously obvious that here you have to modify more tuples than on the left, right? But from now on, I will not treat cardinality repairs. So everything will be about, okay, first another example. Suppose you have this table, you have course, student, prerequisite, and year. And this means that a student like Jones is taking the course Computer Science 402, and a prerequisite of this course is Computer Science 311, and he took this prerequisite in this year. Yeah, when I used these slides also at the Dutch Tool seminar, and someone was asking me, why are you using years of the previous century? But the reason is, well, one reason is I'm old, and the other reason is that I was inspired by the text from Jeffrey Ullman, which uses probably years in the 80s, right? Okay. And so that's the meaning of the table. And the second constraint states, this is tuple generating dependency or an embedded multi-value dependency, stating that basically, well, you can read it, but what it means in English is that every student should take all prerequisites of a course. Huh? And this table is inconsistent because, first of all, the first two tuples, like Jones has taken this course in 2 different years. So these two tuples are conflicting. And there's another inconsistency, like if Smith is taking this course 402, and if Computer Science 311 is really a prerequisite, then Smith should have taken it, right? So how can we repair this database? Well, there are multiple repairs. both tuples here, both tuples with a dagger and the double dagger. If you delete these two, then that's fine. You only keep the last two tuples. And this means that the only prerequisite of the course was 401 and everything is fine. Or you can delete either of dagger or double dagger, but then you should also delete the tuple about Smith because he has not taken the prerequisite 311. Or you can delete one of these two, dagger or double dagger, and insert a new tuple saying that Smith took this prerequisite course in some year. And whatever year it is, I mean, you can choose the year, right? And this means that you have an infinite number of repairs, right? Because you can pick any year. That's fine. This would be a symmetric difference repair, yeah?
Does it mean that you can make up data to force your repair?
Yeah, you can. Yeah, you can, but the point here is, I think that if you do consistent query answering at the end, you will take the query on, you will execute the query on every repair and take the intersections. So these like made up data, they will never occur as a consistent answer. I think that will be more clear later on also, but yeah. And the point is that we actually, remember the first slide by this big Q, we actually never want to compute these repairs. We want to directly execute the query on their own original database. Right? Okay. Yeah, this example came up in a paper POTS paper we had at POTS this year. It's a little bit counterintuitive here. That's why I put it here. Like, suppose we have two constraints. The first one is a tuple generating dependency or an inclusion dependency. This means that whenever I have x, y, then I should also have y. And so this means actually that, yeah, it's an inclusion dependency, right? And then whenever I have s, y, z, then z should occur in T. And here I have a database that falsifies the constraint because, okay, B is present here, but C is not present here. So how can I repair this database? I just add C. That's one possibility. Now I show you another possibility that might look counterintuitive. So what I can do is I can simply delete the tuple BC, add the tuple B with some new value I invent, bottom here, and then I add bottom. And intuitively, one would think that, well, this is, if you compare S and R, you would think that maybe R is closer to the original database than S. But that's actually not true, because if you take the symmetric differences, like for R, I have to add these, T of C is in the symmetric difference. If I compute S, what did I do to obtain S? I deleted the tuple BC, which is so in the symmetric difference. I added B bottom and I added T bottom. And now the point is that these two are not comparable by set inclusion. So they are both good symmetric difference repairs. Okay? So just to show that sometimes things may be a little bit counterintuitive. Of course, here there's another repair where you just have three empty relations. Okay. And then when looking at this example, you may say, well, maybe there's could be another notion of repair where you say, and I think it also makes intuitive sense, where you say, I want to have a repair that preserves as much information from the original database as possible. And if you look at the literature, that is actually something that has been proposed, what is called loosely sound semantics, by the people from Rome a long time ago. And the idea is there, you just try to maximize the set of preserved database facts, or you minimize the number of deletions. And moreover, you could, even in searches So do any number of insertions. I will come back to that later, why that can be sensible. So this is called the loosely signed semantics. And just like you say, R is preferred to S if R preserves more database facts than S, or the same set, right? And you don't look at insertions. You say, if you look at the facts that are in R but not in DB, and S, the facts that are in S and not in DB, this can be anything. And this is kind of, you have seen this already also in previous slides. You can say this is the open world assumption, that you're not penalized for adding things. You're only penalized for deleting things. And you may find this strange, like, does it make sense to allow any additions whatsoever? But then maybe, I mean, if you think about it, even if you want to do consistent query answering to conjunctive queries, if you have a repair R and then a repair R where this is like disjoint union, you add delta, which can be anything, which can be superfluous addition, which can be garbage. But if you do consistent query answering to conjunctive queries, remember we take the intersection of the query on every repair. So if you have this repair and then this repair, and take the intersection, I mean, the only answers that can be consistent are the ones that are in R, right? Because conjunctive queries are monotone, right? So from that perspective, even you can say, okay, you can allow additions, whatever you want. If you do consistent query answering with respect to monotone queries, that's fine. I mean, you could try to fine tune this in, this is actually a repair notions that, well, I think it's an exploit. I could not find any paper where they do exactly this, but it makes sense from a database perspective. Like, suppose you take just the loosely signed semantics and you say, okay, and I want to have a minimal number of insertions. Even though we have seen that adding superfluous insertions is not that important, but I can say, okay, let's have minimal number of insertions. You can define something like this. I call it here max intersection repairs. You say R is preferred to S if the first thing is that R preserves strictly more facts of the database than S. And the second bullet here states, if R and S preserve the same set of database facts, then I prefer the one that inserts less tuples. Yeah, there's a question. Yeah.
In general, when somebody explores it, what do? They define this repair and then what?
Well, they can do consistent. They can do consistent query answering with respect to this notion, for example.
Yes, but I mean, it's just a problem statement, right? And then.
But maybe I should have said the unused, or I couldn't find any paper where they use exactly this notion, which makes intuitive sense to me. Like you want to keep as much, and then you do minimal insertions. Whereas like symmetric difference repairs, they treat insertions and deletions on the same level. That's what symmetric difference is about. Now you could think intuitively it makes a lot of sense to say, well, no, I consider deletions more harmful than insertions, to have an asymmetric treatment of insertions and deletions, right? And probably this will change maybe some complexity results on consistent query answering, right? And if you define it this way, then you can easily prove that every max intersection repair is a symmetric difference repair. So you're just restricting the set of symmetric difference repairs to something that's maybe more meaningful. I don't know, right? And then if you take TGDs, then in this way, you could also always repairing by adding tuples, and we will come back to that later. But because if you have a TGD, you would say, okay, maybe it's the most natural way to repair is not by, if you have a violation of a TGD, you could delete tuples, but you could also say, no, let's only add tuples, which makes sense, right? You preserve as much information as possible. Okay. So here in this notion, like, again, this database, for this database, if I would use max intersection repairs, then I would say I have two possibilities. I delete the first tuple or the second tuple, and then I add a tuple stating that Smith has taken the prerequisite 311 in some year. Okay. Then value-based repairing. So you could say why the idea of value-based repairing is that if you have like long tuples in a database and there's a mistake in the tuple and you throw away a tuple, then you may also throw away good information in the tuple. And tuple-based repairing, you throw away a tuple because it has a bad value in it, but you also lose the other information. So the idea is, can't we come up with a good notion of value-based repairing, where the repair primitive is not deletion or insertion, but rather like updating a tuple. And here's an example, like suppose every course is taught by one teacher. That's the first functional dependencies. And then if I have a teacher in an hour, there's only one course. This is the classical example that shows the difference between BCNF and TurtNF. You may have seen it in your database course. So the second means that a teacher cannot teach two different courses at the same hour. And here it's violated because you have, again, Dave Meyer and Ullmann teaching the course 402. And in tuple-based repairing, you would say, okay, I can delete one of the two tuples here. I deleted the tuple about Ullmann. But then you might say, oh, yeah, but maybe it's true that the computer science course is taught at 2 moments in the week, on Monday and on Friday. So maybe, what about this this repair, like saying, okay, I just want to say, okay, Ullmann was a mistake and I put Meyer instead, and I preserve the information that this course is also taking place on Friday. Here we assume that the course can take place at several hours, more than once in a week, right? And I think this makes a lot of sense. And probably you would have another repair where instead of having 2 times Dave Meyer, I would have 2 times Jeffrey Ullmann, but I would preserve the information about the hours because there seems to be no mistake in the hours. Yes?
Sorry, for my question. Earlier on, you completed the data with tuples, but what will you complete with null values?
Yeah, in this case, I assume we have, in all this talk, in all this work, we assume no null values. Yeah. Yeah, maybe next slide, I have a kind of null, but there has been work, Leo Bertossi has done a lot of work about repair, about null values, and yeah. Right. So we just to make the point that, yeah, maybe you just want to update the value, right? And this repair, as in all repair notions we have seen so far, it will not be preferred because we insert a new tuple, right? And on the other hand, you may say it's natural because I want to preserve, this S preserves the information that there is a course taught by at Friday 10 a.m. And I have an old paper doing this, but it's quite complicated if you want to do this value-based repairing. I will not go into detail, but this is the main idea, I think. And now again, we have this relation where you have bosses that have to earn more than clerks, and I have these two tuples, and now I want to have a repair like this, where I say, okay, either I update this 20 into 40, or I change in the last fact, the fact that Anne is a clerk, I say she's a boss, right? And I want to do something like this, where I combine values of two tuples. And actually the way we did this in this old paper is like, if you compare what's preserved about the database in this repair, instead of just looking at the level of tuples and intersection, you can look like tables with a kind of, these are not nulls, but these are variables. And then you can look at homomorphisms, right? And if you look at this table, like this table is homomorphic to the database, and it's also homomorphic to the repair. Right? So because it's homomorphic to the repair, you can replace y by 40 and x by boss, and it's also homomorphic to the database. And so you could look for repairs such that instead of taking, like if you take the intersection, of course, you get something that's homomorphic to this one, but we were looking like trying to keep as much information as possible with respect, not with respect to set inclusion, but with respect to this homomorphism relation. Okay, I hope that's more or less clear. I will not take it any further here. Okay, maybe, well, just there has been a lot of work on repairing numerical attributes. Maybe I skip this for, you can read the slides, it's not so important. I just want to do the important things first. If I have time enough, we can come back to this. I want to talk about the problem of repair checking, right? And this will always be with respect to symmetric difference repairs. So this is the problem of repair checking. So you have a finite set of integrity constraints, and repair checking always with respect to symmetric difference is the following problem. Your input is a database and a repair, and I assume the schema is fixed, and you are asked whether R is a symmetric difference repair of the database, right? So notice that this is data complexity again, because we assume that the constraints are fixed. And then we have to define what is the complexity of this problem. And it's defined often with respect to a class of integrity constraints. So assume that you have IC, it's just a class of integrity constraints. For example, all functional dependencies or all including dependencies. And you fix a complexity class C. Think of C, for example, as P or coin P, and you say that this problem for this complexity class is, and you have an upper bound and a lower bound. The upper bound, you will say that it is in the complexity class if whenever I take a finite subset constraints in this class, then the repair checking problem is in this class, right? That's the upper bound. And then for the lower bound, we say that it's C complete if it's in C, so we have an upper bound, and there exists a finite subset of constraints such that the problem is C complete. What's important here is like we say that it's C complete if it's C complete for even for one fixed set of integrity constraints, right? I will give some. So for the upper bound is fine, it should always be in this class. For completeness, it's sufficient to have one case where it's hard, right? Okay, I assume you know these complexity classes. Maybe I will, FO is just the class of problems you can use, you can solve by using predicate calculus or relational algebra as a programming language. Maybe CoMP. CoMP, you can define it in terms of Turing machines, but here we have like this definition, like a problem is in CoMP if whenever you have a no instance, I mean an instance of the problem where the answer is no, then you have a succinct disqualification, right? So this means you can prove that the answer is no by a small certificate called the disqualification that's verifiable in polynomial time. So, and actually this is the picture we get with this for all these complexity classes we have seen. So what does it state? So here we have like for love and inclusion dependencies, it's in a polynomial time, repair checking. Here we have in log space, deterministic log space, up to denial constraints. And then if we move to here, universal constraints, tuple generating dependencies in F4, then the problem is in CoMP, and it's actually CoMP complete already, right? Which is actually very bad news because this seems to say that whenever you have TGDs or universal constraints, even repair checking whether something is a repair is already CoMP complete in data complexity. But beware, this becomes CoMP complete even if you just find one set of constraints in this class for which it's CoMP hard. Yeah? I don't know. Yeah. Actually, I didn't even check all these proofs. They were actually in the paper, and some of these proofs are very easy, and some of the proofs are, yeah, it's something to look at. But so, yeah, first thing I could say, these are all in CoMP, so this could be a question for the students. Why is it always in CoMP for first order constraints? Yeah. So if, to be precise, if something is, if the answer is no, if R is not a repair of the database, then there is another repair that's closer to the database, that's consistent, and that shows that the original repair candidate repair was not a repair, right? So this is what I state here. So assume that you have this input and it's a no instance. Well, then I have a succinct disqualification. What is it? It's just a real repair S, which satisfies this property. It's closer to the database with respect to symmetric difference than R, which also means that, remember the two inclusions I had, that is polynomial size. It cannot be larger. And it has to satisfy the constraints. Now we have seen that testing this in the constraints of first order, this can just be done in polynomial time. Okay, so this shows that everything here should be indeed in CoMP. For denial constraints, what could be the reason why this is in log space, upper bound? Or even a polynomial time, how would you check that a repair is a candidate repair is a real repair with respect to denial constraints? But we have seen that denial constraints, you can only repair it by deleting tuples. So if you give you a candidate repair, you will first check that it's indeed included in the database, that it's consistent, otherwise it would not be a repair. And then you have to make sure that whenever I add another tuple of the database, then it should become inconsistent. So the only thing you have to try is to insert one tuple at a time. And that's what's stated here. Like, why is this in L? Well, if something is a symmetric difference repair, then it means it should satisfy the constraints. It must be included in the database. And then for every tuple in the database that's not in the repair, that has not been preserved, you have to, if you add it, then it becomes inconsistent. And this you can do in log space because you just need an index over the database, right? So, okay. Now, if you look at this figure, and these are almost all the results that have been obtained, you can say this is unsatisfactory for two reasons. And the first reason is, of course, that it is always limited to one set of constraints, like, for example, only in inclusion dependencies, only functional dependencies. But as we have seen in the first course already by Andreas, that typically in a database, you have a combination of inclusion dependencies and functional dependencies, for example. So it's not, I mean, these results, they do not reflect the real situation in database systems where you typically combine different classes of integrity constraints. And actually, this is an open issue. What happens if you take integrity constraints from multiple classes? That's one thing. So that's what I see the first open challenge, like even what happens if you have, for example, primary keys together with foreign keys, including dependencies together with functional dependencies together with inclusion dependencies. The only result I could find in the literature is this one, is that if you take FDs and inclusion dependencies together, then repair checking is already co-MP complete. So this means that even if you think that inclusion dependence its polynomial time, FD is even in log space, but if I take them together, it becomes also co-MP complete. So. Another more interesting question is probably, okay, it has to do with the way we define it. It's already complete if it's hard for the class for one set of constraints, right? But maybe this is a very weird set and does not occur in practice. So what we actually would like to do is the following problem. So if you look at this set, all these problems for any set of constraints sigma from this complexity class, can we decide, given such a set, whether it's in P or, for example, co-MP complete, right? Like, can we have some kind of dichotomy theorem? We have seen several dichotomy theorems already. So can we decide it for every, so can we decide the following problem? So I give you, I fix a set of integrity constraints, and then I give you a set of constraints, and I ask you to decide whether it's, for example, in P or co-MP complete. And we will look into more details into such a problem after the break. So now I come to, I mean, for me, even the more interesting part of this talk is really about consistent crayons. And up to now, it was just about repairs and repair checking. So all we will do is talk about conjunctive queries. So we have seen already conjunctive queries. They all have this form. And we have also several times already seen what it means to be self-joint free. So a conjunctive query is self-join free if the same relation name and as we have seen in the talk of Antoine and probably also in the talk of Nicole, that often we can obtain nice results for self-join free queries that do not generalize to queries with what we call self-joins. And such a query is so Boolean if it does not contain any free variables. So often also for in the theory, we will restrict ourselves to Boolean queries, right? So now what's the precise definition of consistent query answering? Again, with respect to symmetric difference pairs. Now I fix a set of integrity constraints. I fix a Boolean query Q, and this is a problem. So CQA stands for consistent query answering. Sigma Q is the following problem. So the input of the problem, the instance of the problem is a database. Again, the schema is fixed. And I ask you whether Q is true in every repair of the database. Yeah, before I was talking about taking the intersection of every repair. If the query is Boolean, then it's simply asking whether the query is true in every repair. True and true and true and true for all repairs. So also importantly here is like, for every set of constraints and every query, we have a new problem. And the complexity is really data complexity. And then the definition of complexity is the same. Now, let us fix a class of integrity constraints, like, for example, functional dependencies or inclusion dependencies. We say, okay, let C be a complexity class. And we say that the symmetric difference consistent conjunctive query answering problem for this class is in C. If it's in C for every set of constraints and every query. And we say that's complete if, again, there is at least one set of constraints and one query such that it's complete for the class. Right? And again, you will see we have the same, you will have the same complaints as before with repairing, because, okay, the first thing is we are assuming that IC is just one class of constraints. So we are not looking at, for example, inclusion dependencies and FDs together. So that's one complaint you can have. And the second complaint is it becomes hard for a class as soon as we have one witness where it is hard, right? And this is the picture we get. Yeah, so it means that even for like the most easiest case, just key dependencies, it becomes already CoMP complete. And I will show you why this is the case. And here it's like for universal constraints and weakly acyclic TGDs, it's pi2 complete. And for TGDs, it's already undecidable. I assume this is related to the fact that the termination of the chase is undecidable. And the only thing where it's in P is LAF TGDs in inclusion dependencies. And I guess the reason here is that in this case, if you take the intersection of all repairs, there's one repair that's included in all the other repairs. I think whenever an inclusion dependency is violate, you can always delete tuples. And in that case, you will find one repair that's included in all other repairs, and that's the one that gives you the consistent answer. Right? And if you compare both, so again, if you know that repair checking is in polynomial time, then you can deduce from it that consistent query answering can go at most QMP complete, right? Because of this, the existence of this witness, this repair, falsifying repair that can be checked in polynomial time. And actually it's the case that, yeah, again, the only thing that's hopeful is this side, right? But again, this is because, for example, for keys, there's just one set of keys and one query for which is hard, right? And okay, I show you why this is the case. And this will also be important for what I will tell you after the break. So I just claim that it's going to be hard for this set of constraints. It's just one functional dependency. It's a binary relation, just one functional dependency. Vertex determines color, and this is the query. Like it's a conjunctive query, and of course it's not self-joint free in this case. And what does intuitively, what does it tell you? Think of this. This is a graph, and this is a way of encoding the graph. And for every edge, you see we will have a reduction from recolorability. So for every vertex, I introduce 3 tuples, red, blue, and yellow. These are my colors. And then I have an edge relation. So I just store like there's an edge between 1 and 2, 1 and 3, and so on. And now what's the constraint telling me? It's every vertex should have at most 1 color, right? So in a repair, I have pick a color for every vertex. And the query is actually asking whether there is an edge between X and Y such that X and Y both have the color Z, right? And now it's almost obvious that the graph is 3 colorable even only if Q is false in some repair, right? I show you, for example, in this case, the graph is 3 colorable. Here's a coloring of the graph. And my repair simply says the first vertex was blue, the second red, the third yellow, and so on. And now the query is false in this repair because the query asks whether there are 2 vertices that are connected and they have the same color, which of course will not be the case if this is a valid 3 coloring. So this actually shows that that here this is QMP complete, right? Just because this simple example. But of course now you can ask, yeah, but aren't there many cases where this will be tractable? It's not because that we have one case where it's QMP complete that we have to be hopeless. Right? I'll tell you more about that after the break. Also, for full TGDs, again, you see for full TGDs here, consistent query answering is QMP complete. And also you can say, yes, that's because you allow deletions. Because the full TGD, you can make a repair by just chasing the database. And we know if it's full, then the chase will terminate. And actually that would be a good repair, right? And the chase terminates in polynomial time and you just execute your query. But the point is that if you take symmetric difference repairs, then you also delete. So the repair obtained by the chase is not a unique repair, right? Okay. So again, these are the complaints again. What if you combine classes of integrity constraints, and for example, a very natural thing to do is just combine primary keys and foreign keys, right? This is not in this picture, right? Because the keys are here, and the foreign keys, they are kind of including dependencies. Yeah. Yeah, I don't know the exact answer, but I looked into the paper, and what happens is that yeah, you have a minimal repair that's including. So actually, there's if you do consistent query answering for conjunctive queries, then the consistent answer is completely determined by the smallest repair. So you can, if you can compute the smallest repair, then you just have one repair and you execute the query on the smallest repair. Yeah, yeah, yeah. And again, that's what we will do also after the break. Like, okay, if I give you now this, I say I have a segment Q. Even though I know that for this class of integrity constraint, there is a case where it's, for example, be complete. Can you tell me the complexity for every individual set of integrity constraints and queries? So is there really a dichotomy between P and P, for example? And yeah, maybe I should recall here, like, what's the point of dichotomy theorems? One of the things is that if P is different from NP, then you have problems by Leitner's theorem that are neither NP nor NP complete, right? So the idea is maybe could there be, for example, here a problem that's neither NP complete nor in polynomial time? Well, that would be surprising. But can you really prove the dichotomy, right? And we will see such a dichotomy result after the break. So I still have 5 minutes. Okay, let me. So this will actually be our focus after the break, where I will only consider that sigma is a set of primary keys and Q is a self-adjoint-free Boolean conjunctive query. And for that class of constraints and that set of queries, we will show the existence of such a dichotomy, right? Okay, I think I stop here and yeah.
Just a remark on the you have no intermediate classes. But it also says that in a sense your algorithms are complete. You are not missing any algorithm. You give solutions for the practical cases.
Yeah.
They cover everything that you can do. There's no magic outside that.
Yeah.
You do not make any further assumptions.
Okay. Yes.
Right? You're saying the different things about the identifying the intermediate classes?
Yeah, but yeah. Yeah, okay. Any other questions? So then, that's right. Yeah, we have a break now. Yeah. Up to. We can, yeah, because this is a new. Yeah. In this second part of the talk, I want to talk a little bit more about this part. Like we know that for key constraints, consistent query answering to conjunctive queries can be complete. You could say, well, this is very bad, but then again, this is just for you have seen one particular query and one particular key constraint for which is complete. So now the question is, can we look at the complexity? Can we decide the complexity for any combination of key constraints and conjunctive queries? So that will be the second part of my talk. And actually, I will not even talk about keys, but I will only talk about primary keys. And what it means that I assume that I have one fixed key dependency for every relation. So for whenever I have a relation R of a certain arity, I will assume that there's one key dependency, which is like the positions 1 to k determine all other positions. It means that the first k positions will be the key, and often it's called primary key because that's the only key, right? And if I talk about keys, and I mean this primary key, and we also say in that case that the signature of the relation R is nk, where n is the arity, and k means that positions 1, 2, 3 up to k are the primary key. And well, the remainder is just like, okay, we have atoms, we have, you know, we have seen this before, we have facts. A fact is just an atom without variables. Oh, this is important. We say that two facts are key equal if they agree on their relation names and they agree on all key positions. So that our two facts are key equal if they conflict on their primary key. Like, for example, here, SABD and SAB. Oh, okay, they're also key equal, but you imagine that what I wanted to say is ABE, yeah. But the fact is key equal to itself, so it's not a mistake. And also I will underline the primary key position, right? And then a database is just a finite set of facts, and the notion of block has been introduced already by Antoine this morning. It's just a maximal set of key equal facts, right? And then a relation, you know what is a relation, and a database if it's now consistent if it does not contain a block with two or more facts, right? And a repair now will select exactly one tuple from each block. So what does this mean? For example, if I have a relation S here, I have two blocks. The first block has the key AB, and the second block has key BC, right? And now to make a repair, I just have to pick one tuple from the first block and one tuple of the second block. So in this case, repairing is very easy. And of course, here you have 6 repairs because I have 2 choices for the first block and 3 choices for the second block. And what's nice, if you only have primary keys, that symmetric difference repair and cardinality repairs, they coincide. Because every repair will have the same number of tuples. And that number of tuples is the number of blocks in the database, right? And of course, since keys are denial constraints, adding tuples will never give you a better repair. So everything is very clear in this setting, right? So you know what's a Boolean query. I will often look at the Boolean query as just a set of atoms. So this means that I will not forget about the existential quantifiers. And of course, like D here is a constant, X, Y are always variables, A, B, C, D are constants. And so this is just a shorthand for there is X, there exists Y, this conjunction is true, right? Also later on, I will often need 3 variables. So if I start from this query and I want X to be free, then I just put it in parentheses. And then it means that if I write Q of X, then I mean Q is the free variable, right? And a conjunctive query is self-joint free if no relation occurs more than once in it. Okay, we have seen this. So now I can define a certainty Q. So I fix a Boolean query Q, and often this will be a self-joint free conjunctive query, but assume now it's just a Boolean query. I define certainty Q as the following decision problem. So certainty Q, the input is a database, and the question is simply, is Q true in every repair of the database? The first observation is, you may wonder, yeah, where are the constraints? Well, I assume that Q has atoms in it, and the constraints are just the primary keys associated with the relation names that occur in Q. So I don't have to repeat the constraints. If you really want to see the constraints, then certainty Q can be seen as a shorthand for this problem, where these constraints are just a set of all primary keys, right? The second observation is we study data complexity. So Q is not part of the input. It means that for every Q, we have new problem. Also, if the answer to this question is yes, then I will call the input database a yes instance of the problem, and otherwise it's a no instance. Right? And in the remainder, we will say that we will restrict Q to be self-join free. Right? So this is the set of problems we are interested in. For example, I start with a simple example, and we want to, the idea will be now, can I determine the complexity of this problem for every Q? So I give you a self-join free, and I ask you, what's the complexity of certainty Q? That's the problem we want to solve. Not just saying that there is a set of primary keys and a query Q for which this problem is QMP complete. I want to know the complexity for every Q, right? And here's an example. So if I ask you for this query, you will say, oh, for this query, it's in FO, right? This could be an exercise, but if I ask you, when is this query true in every repair? Now look at the possible database. If I have a database like this, a relation like this, it's clear that here I can make a repair where this query fails because I pick here AE, and I pick in the second block BF, and this is a repair where D does not occur at the second position, and I have a falsifying repair. So when will this query be true in every repair? Well, if there is a block that contains only one tuple, and the second position of that tuple is a D, right? But this I can express in first order logic, right? So here's the proof. The following are equivalent. Q is true in every repair, and the database satisfies this expression, right? There is a block S with primary key Y, and all the tuples in that block have D at their second position, right? This is actually this query in the beginning, my fifth slide. I think this was actually the big Q, the uppercase Q. So we know that, okay, for this query, it's in FO. This means we can solve it by just using first order logic as a programming language. And that's nice. And actually, we will be interested in queries for which this is in FO. And why is that? Well, because in the database systems, we have SQL. And if it's in FO, you can just translate this in a SQL query and just execute it on your inconsistent database and get the consistent answers, right? So this FO boundary will be important for database people. Okay, now we have seen an example where the problem was QMP complete, but remember this was by this graph coloring, and we ask whether there are two vertices with the same color, and this was a self-join. So now we want to restrict ourselves to self-join free queries, but even for self-join free, you can prove that it's QMP complete. And for example, I will argue that for this query with two atoms, the problem is QMP complete. And the reduction is from monotone SAT. And also you will see that this proof is quite straightforward. So assume you have a monotone SAT formula. This means you have a SAT formula, but in every class you have only positive literals or only negative literals, right? And now I can encode this into an instance of certainty Q for this problem. And the P, you think of it of being the positive classes. So in P, I term the first class is P or Q. The second class has negative literals, so I do in the second class P, Z, in N, and so on. And then I claim that this formula is satisfiable even only if the database has a repair that falsifies the query, right? And why is that the case? Well, from top to bottom, assume that this formula is satisfiable, then this means that I can pick a literal from every class without picking at the same time P and not P, right? But that's actually a repair. If I do the same things in a repair, then I will have a repair that falsifies the query because I will never pick positive Z and negative Z, so to say. Okay, if that was not clear, just think about it. And the inverse is also, so if I have a repair that falsifies this query, in a repair, I must pick a value of top. And if I falsify the query, this means that if I pick, for example, 1P here, I cannot pick P in the negative, in the N relation, right? So, okay. So this is QMP complete. And now this is, so our complexity classification task is now the following. So as I mentioned, I give you a self-joint free Boolean conjunctive query as input. And I ask you determine lowering upper complexity bounds on the complexity of this problem, right? And what are nice complexity classes is like F4, log space, non-deterministic log space, P, QNP, right? So we change the problem a little bit. So now I give you as input a query and I want you to tell me the complexity of certainty Q, right? And we already know some results. I just chose, so from S, Y, D, you can tell me, okay, it's in FO. And for this query, you tell me it's QMP complete. We have proven it. But now I want, the question is, can we complete this table for every self-joint free Boolean query? That's our task, right? And that's much more ambitious than what we have seen in before the break, where we just say, okay, for keys, it's going to be complete. Here, the point will be that, okay, yeah, but I have to give the complexity for every possible queue, right? Now, I already mentioned that we will often be interested like in this class FO, first order, because that can be implemented in SQL. Now, in general, and this is about descriptive complexity. So instead of just fixing a classical complexity class, we can also ask, remember this big Q, can we express it in some logic, right? And so let's L be some logic. And like Q, a query, a conjunctive query with 3 variables. And now I will say that a consistent rewriting of this query in the logic L with respect to primary keys, that's a formula with the same 3 variables, such that for every databases, the following are true for all constants, saying that for these constants is a consistent answer. It means this is true in every repair of the database. It's the same as saying this formula for this constant is true in the database. You see what's happening? So my problem was to ask whether this C1 to Cn is a consistent query answering, whether it's true in every repair. And I find a new formula, phi, in my logic, which I can execute directly on the original database, right? And I will call this the first order writing in this language. By the way, in many papers, they just state rewriting in, for example, first order. Actually, it would be better to say a consistent rewriting in this language with respect to primary keys, right? Because of course, this Q and this formula phi, they are not logically equivalent, right? So the gray color text here, I don't know whether it's clear. Yeah, it's often implicitly understood. Rewriting in first order logic is often called first order rewriting. And of course, the interest of first order rewriting is that you can implement it in SQL. And now if Q is just a Boolean query, then saying that Q has a first order rewriting is by definition the same as saying that certainty Q is in F4. You can solve it by a first order query, right? Yeah. Probably if yeah, because the problem is in CoAMP, probably you can second order logic. Yeah, you can specify repairs in second order logic. Yeah, yeah. But of course, here we are interested in like first order logic. If possibly, like for example, it could also be an interesting logic. Okay, so this is really a very important definition. And so it's, instead of talking about a complexity class in terms of Turing machines, it's really about complexity in terms of a logic, which we call also descriptive complexity. Yeah. 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 But exactly the point is that you give me Q and I tell you what's the logic you need for this formula. Yeah. And hopefully there will be a lot of Qs where I can do it in first order. Because, okay, coming back to this example, this was CoAMP complete, but you see, it's, you can say, well, this is a strange query if you think about it. This is a join on a non-key position. Which, I mean, in relational databases, often joins are foreign key primary key. And this is not like this. So you could still be hopeful here and say, okay, maybe it's only CoAMP complete for queries that are a little bit weird, which actually we believe will be, okay, I'll show you. So let's start to be interested in this first order rewriting. So I want to have this FO binary. I want to know whether a query, you give me a query Q and I will tell you whether or not it has a consistent first order rewriting. And we are interested in that problem because first order, you can translate it in SQL and directly execute it without having to repair the database, right? Now, again, I could start. Let me assume I have a self-join free conjunctive query and I have this atom, where C, I just took an atom with a constant key, that's important, so a key without variables. And I just take this one as an example, but you can easily generalize. And then I have a second position. I just chose to have a constant to show that that can be a constant, and then two variables, the same variable and a Z, just to have like something that's representative of all possible combinations. Now you may wonder when will that query that contains that atom, when will it be true in every repair? Now think of a database and the query is self-joined free. Now suppose I have a block. The first thing, of course, it can only be true in every repair if there is at least a block with C's. Because if I don't have a block with C at the primary key, then it will be false in every repair. And then I look at that block, and if I have D, A1, A1, B1, you see this A1. Here I repeated the constant and the variables. Okay, this one can possibly make the query true if I set Y to A1 and Z to B1. And the second tuple is also good. And now what about the third tuple? Suppose in this third tuple, in this box, I had like something that's not D. Then I can build a repair that falsifies the query, right? I pick in my repair that tuple where this block, this value is not D, right? And another, suppose here now, suppose this one is D. Now look at this. If at this position, I have a constant that's different from A3, like say 44, then also I can make a falsifying repair by picking this block. I take 44, and 44 is not equal to A3, right? So now this is actually, we can now formulate this in first order logic, everything I told you, like, okay, I will need also Q prime is Q minus this atom, right? And Q prime again will be a self-joint free conjunctive query where I have just removed the R atom. Now, the following can now be seen to be equivalent. That was what I claimed to be true on this example. Like Q is true in every repair, and the database should satisfy. The first thing is there is a block with C as primary key position. And then I must say something that for all tuples in the block, whenever I have a tuple like this, think about it as being this tuple here, the third tuple. What must be true? We have seen that to be true in every repair, U2 must be equal to D. This was this position. And also this position, which corresponds to U4, must be equal to Y. And now I fixed, so to say, the values for this and this, and the variable that's still in the remainder of the query. Now I have a value for Y, and I have a value for Z, and I add now a formula which is phi YZ with three variables Y and Z, and I say that it's sufficient and necessary that phi YZ is a rewriting of the remainder of the query. You see why that's true, because it's self-joint free. So for every tuple here in that block, should respect these conditions, that the second position is D, and then the third and the fourth position are the same. And if I pick that tuple in the repair, then I fix the values for Y and Z. And for these values of Y and Z, I must repair the remainder of the database and find a satisfying repair, right? And if you think about it, this will work because the query is self-joint free. I will not, later on in the query, I will not see this R atom again. You see what's going on? So it's simple. And finally, for all quantifiers here, they just run over all tuples in the block, right? Yeah, what's a little bit tricky here is that I want to have Y and Z as the free variables, because you could, and that's because I don't want to rename the variables. So I really want to continue with Y and Z, because these are the variables that can show up later on in the query. That's just a small trick. In this way, if you do it this way carefully, you avoid having to rename variables later on in the query, right? Okay, so this means if I have an atom with a constant primary key, I can get rid of it in a rewriting. Of course, you still can ask whether this rewriting exists, but if it exists, I'm done, right? Now, I've to introduce the notion of reifiable variable. And okay, let Q be a self-joint free Boolean conjunctive query. We say that the variable in X in Q is reifiable if the following holds. For every yes instance of certainty Q, and remember that a yes instance is an instance where every repair satisfies the query, the following, there is a constant C, which can depend on dB, such that this query is true in every repair. This, yeah, I didn't explain this, but this means you take the query Q and you replace all occurrences of X by C. So what does this mean? That means the query is true in every, you pick a variable, you ask whether it's verifiable, and you say, you define that it's verifiable if for every yes instance, there is a constant such that I can fix this variable to C, to a constant, and that's query is also true in every repair. I will give some concrete examples later on, but so this means, why did we call it verifiable? It's sometimes you take this variable and you, well, I don't know what verify exactly means in English, but you make it like, you reify it, right? Maybe a logicians will call this like a kind of Skolem constant, or, okay, Skolemizable could be an alternative. And otherwise I say X is not verifiable. Right? And for example, I will see like you can see like in XY, SYD, X is verifiable, but Y is not. Think about it. If this query should be true in every repair, then intuitively I need to have one value for X, one block, and then for every tuple in the block, all possible Y values should join with the S fact that makes the remainder of the query true. If that was not clear, I'll come back to that on the next slide. But that's my claim. Now, I still have a verifiable atom. It's just an atom where the primary key is verifiable. Every atom in the primary key is verifiable. Okay? So let me, so here I claim that Y is not verifiable, and I show you by an example. Y is not verifiable. Now, this is a yes. So here I have an R relation with two conflicting tuples, like the S relation is consistent. And this is a yes instance because either I pick the first tuple in R and then I make the query true by going C1D, which is in every repair, or I pick the second tuple and then I have another repair where this is true. So I have two repairs, both repairs satisfy the query, so it's a yes instance. But I use different values for Y. In one repair, I need C1, in the other repair, I need C2. So Y is not verifiable, right? But I claim here that X is verifiable, but because you should find such a block. And if there's not one such single block, then you can always find a falsifying repair. Okay? So there are two repairs, both satisfying Q. So it is a yes instance, but there's no constant C such that this query replacing Y by C is true in every repair, because I need, in one repair, I need C1, in the other repair, I need C2. Now, why do we need these verifiable atoms? Now think about it. I take a conjunctive query, and now I have again an atom, but now the key is no longer a constant, but you see I put here two variables, Y, Z, and now I tell you Y and Z are verifiable. Don't ask me how I know this. Suppose I have proven that Y and Z are verifiable. Now I can do, I'm going to do a first order rewriting. I say the following are equivalent. Q is true in every repair of the database, which is equivalent to saying that DB is a yes instance for the certainty Q. And DB satisfy there exists a Z, and then psi Y the Z, where psi Y Z is a rewriting of the query. This is exactly what verifiable means. You see, you have to rewrite this atom, you know that's verifiable. So for every database, I can find a Y and I can find a Z such that this is true, right? That's the idea of being verifiable. And now the crux here is that if I look now at, so now I just need a rewriting of Q where Y and Z has become free variables, right? And now the crux is that in this query, I still have this atom, but now Y and Z, this atom contains in the primary key only constants and free variables. And we can apply the rewriting of variable free keys we have seen before. Now here you might wonder, but is this true? Because this is not variable free, right? We have constants and we have still variables, but now these variables are free variables. Well, the good news is that if you create self-adjoint free conjunctive, then the free variables can be treated as constants. And this is a claim, it's not too easy to understand, but accept the claim for now, right? So if you are not happy with it, the claim that in a self-adjoint free conjunctive query, free variables can be treated as constants, right? So this means that if I have these reifiable variables, I can get rid of them, right? So now I can do this first order rewriting of this query again. How do we construct it? Now I claim that X is reifiable. So the rewriting you can say there must be an X. That's what reifiability means, such that psi X is a rewriting of the query Q, the X Q of X, where X is now a free variable, right? Now I treat this free variable as a constant. So I have the rewriting of there is so there must be a block, an X block, and for all tuples in that block, all RXY, it must be true that. And here again, I have a rewriting of the remainder of the query now. So this formula now phi x the y is a rewriting of the remainder of the query, but where the variables that have been treated, they have to be treated as free variables now, right? Now I have just to rewrite this atom with y a free variable, and of course d a constant, and I can do this, right? That just like there exists such a block with the y. Now y is a free variable; it's treated as a constant, and for all the tuples in that block, it must be that the second position is a d. So I obtain my first order rewriting. If you put everything together, then you get this query, which is like intuitively, it's clear what's happening, right? To make this query true in every repair, there must be a block like this, XU, and for every tuple in that block, I must have an S fact that has Y as primary key, and that actually is a singleton block where the second value is a D, right? So this means that we can rewrite actually such atoms where the variables in the primary key are reifiable. Okay. Now the question is, can we determine whether a variable is reifiable in general? And I just show you some examples about not being reifiable, and then we try to generalize the examples. Like, for example, take this query UX, XY, YZ. Primary keys are underlined, and I'm just claiming that X, Y, and Z are not reifiable. And how do I do that? This is the database. First, you have to convince yourself that's a yes instance. Why is it a yes instance? Well, it has just 2 repairs because there's only one block of size 2. And if you take the first tuple, I mean, S and T, they are just consistent. And either you take the first tuple and the query will be true, or the other repair as the second tuple will be true. And you need different values for X, Y, and Z. You need either C1, D1, and E1, or you need the other tuple, the second C2, D2, E2. So that's what's mentioned here. right? So this actually, if you see this pattern, we will now write something like, we will see R, and I will read this as attacks X. So the atom here, that was the inconsistent one, it had a block of size 2. I will say it attacks X, it attacks Y, and it attacks Z. Basically for this reason, right? And this is still a little bit informal, but we will formalize it later on. But this is to give you the right intuition about what this will mean, right? And so R attacks X actually means that you can have an R block, and depending on the way I repair that block, I have to use different values for X later on. And also we say that an atom attacks another atom if it attacks a primary key of that other atom. So I say R attacks S because R attacks a key variable of S, right? And it's called attack. I don't know why I called it attack like in 2010, and then it remains attacks. You always have to be very careful when you invent a name in your first paper, because that name will survive. And if you're later not happy about that name, then yeah, but attacks is nice, right? It's in my mind, this was what's happening, right? It's a little bit aggressive though. Okay, so in this query, I will say that Y and Z are not verifiable for another reason. Like now, the attack will start from the S atom. So I take, now R is consistent, T is consistent, and S has 2 tuples. And every repair will pick either CD1 or CD2. And then if you pick CD1, you will make the query true for D1, E1. If you take D2, you will make the query true for D2, E2. This shows that, okay, this is again a repetition of what I have just said. But so this means actually you can say that S, this is again the inconsistent relation attacks Y and also attacks Z, right? And again, S attacks T because S attacks the variable Y. It's easy, right? Yeah, and it's intuitive. Now let's try something different. Let's add a new predicate PUY. I see what happens here, PUY, and this is the query I had before. And now I will claim that when I add this atom, then R will no longer attack Y and R will no longer attack Z. And you can imagine why is that? Because I can try to build such a relation that shows that R attacks Y and R attacks Z. So let's try to build such an instance. It will look like this here on the right? You would like AC1, AC2, and then you do the same construction. And of course, now it should be true in every, so you need yes instances. So now you have to add some facts for P. And what would you add? Well, you think that there will be one repair where I go from A to C1, C1, D1, D1. So probably I add AD1 to make it true. But there will be another repair from A, I go to C2, D2, E2. So I will add this one. And then you are in trouble because this is actually not a yes instance, it's a no instance. Why is that? I have a falsifying repair because if I take the tuples with the asterisk, I have a falsifying repair because here I have AD1 and in the repair I take AC2. And so this will make the query false, right? Because the path here goes from AC2 and ends up in D2, but here I have D1. So this is not a proof that there's no attack, but it somehow tells you that I cannot claim that there is an attack by using this database, right? Because this is a no instance. But you see what's happening here, like you had U, there was like a kind of path from U to Y, and suddenly you add another path from U to Y, and that brings you into trouble, right? Okay. And then if I take the same query, then I claim that R still attacks X in this query. And why is that? Again, because I give you a yes instance, and now the inconsistent relation is R. And again, I have RC1, C1D. So I have to use different value from X. In one repair, I use C1, another C2. But now I use just the same value for Y and just one fact, T fact. And so in this case, I have two repairs. The two repairs satisfy the query, so I have a yes instance, but I need different values for X, right? So I write this down here. Okay, so just more or less clear, you know. Now we have to formalize this. This was just the intuition. And normally in the papers, they give you directly the definition, and probably you have difficulty finding out the intuition. It also took me a while before I found out this intuition. And now I come to the syntactic characterization, which basically does this. Right? So I will now talk about the atom. Suppose here I have an atom with relation in R. I can just talk about atom R. There's no confusion because the query is self-join free. There will be only one R atom. And I write vars R for the set of variables that occur in that atom, and key R for the variables that occur at the primary key position, right? And now K of Q, again, think of K as the key dependencies of Q. They are just like all the dependencies. For every atom you add, key R determines vars R. So this is like a functional dependencies, but not among attributes, but among variables. So for example, if I have this query, UY, UX, then K of Q, so the key depends is UY because of the first atom, U determines X in the second atom, X determines Y, and so on, right? And now an important notion is the closure of an atom with respect, the closure of an atom, R plus, with respect to Q. These are all variables that are determined by the key of R, but with respect to the functional dependencies or the key dependencies that occur in all atoms except for the R atom, right? So for example, if I have to compute R plus the Q, it means that we take all atoms that are determined by the primary key of R, which is U, but without using the functional dependencies of the R atom. So I have UY, so I can U determines Y, and Y determines Z, so I have UYZ, right? But X is not in there because I cannot use U determines X. Okay? And we say here that these are the set of variables externally determined by R. It's externally, you take all functional dependencies that are external to R that are not, okay? And now we can come to the notion of this attack. And attacks like assume Q is self-join free Boolean conjunctive query. I write R attacks the variable Z if there exists a sequence of variables like this, such that the first variable is a variable that occurs in R, the last variable is Z, and none of these variables is externally determined by R. And moreover, every two adjacent variables occur together in some atom of Q. And this actually mimics exactly what's going on here. Like we want to have like basically like such a sequence of variables. Here it was, for example, UX, XY, YZ, right? But the problem we had was in this situation, because here like the y, was also externally determined by u, and this created a problem. Yeah. Well, so, example, if I have this tree and I say that the sequence x, y, z shows now that r attacks z, what do we have? R plus q is u. It's only u because, I mean, this is x determines y and y determines z, so the closure is just u. And now I have x, y, z, and x appears in the R atom, so the first condition is satisfied. The variable z is okay, it's fine. This is the last variable in the sequence. And every two adjacent variables, they occur together. Like there's an atom where x, y occur together. That's the S atom. And y, z occur together in the T atom. So the definition is satisfied, and so therefore R attacks Z. And now the point is when I add PUY, then suddenly Y is externally determined by so then Y will show up in R plus the Q, and I can no longer use this sequence, right? Okay, because the sequence is true if Y is not externally determined, but by R, but if I add PUY, then suddenly Y becomes externally determined by R, right? And this exactly captures the intuition I've showed you before. So here are some examples of this attack graph. I will not construct it in detail, but it's a nice exercise to build it. Like, for example, you can find R plus Q. How do you find R plus Q? You start from R, you take all key dependencies in all atoms except for R. And so I start from X. And then, for example, since X determines U, I can add U. And then I have XU, and because XU determines V, I have XUV, and so on, right? And you do the same for the other ones. And then R attacks B, for example, because the sequence is R attacks B because you can find the sequence XY and YZ, XYZ. They occur together, Y and Z occur together here, and Z occurs at the primary position of B, so you have this attack. And actually what it means that you can build a database with two repairs where you have an R block of size 2, and depending on the choice you make in the R block, you have to choose to make the query true for different values, different tuples of B. Right? Okay, and here you see the attack graph has cycles, right? Now I take the same query, and now I will add WAX, where A is a constant. Right? Now what happens if A is a constant? We had this functional dependencies, where you have on the left-hand side the key variables. Here the set of key variables is empty, and you have X, right? So this is perfectly fine for functional dependency to have an empty left-hand side, right? Even though in database courses, normally teachers or professors don't tell you that it's possible, but I mean, it's fine. This actually means this is satisfied by a relation. For example, empty determines A means that in that relation, in the A column, you only have one constant. It's of course not very useful in practice, and that's probably why people don't like to talk about it, but here we need it, right? And then everything changes because now, because you have empty X, so X will enter, when I take the closure now of R, I start with X, no, not R, for example, Z, for example, now Z
can use this functional dependency to, so that B plus has X in it because of this functional dependency. Right? Okay, I just wanted to make clear here that this attack graph is acyclic. Right? Okay, so now we can somehow determine verifiable atoms, so to say, right? Or these are atoms where in the primary key none of the variables is attacked, right? And now I have this theorem, and so let Q be a self-adjoint free Boolean conjunctive query. If the attack graph of Q is acyclic, then Q has a consistent first order rewriting. Now you can tell me why would this be the case? If the attack graph is acyclic, then you always find an atom that has no incoming attack, right? That's true for an acyclic graph. Now you pick that atom and you know that none of the variables in the primary key is attacked. Now we know that this means that this atom is reifiable. So you can do this trick for this atom. You do this trick we have seen before. You do this trick actually. For this atom, you put these unattacked primary key variables in front, and then you do the rewriting for the remaining of the query, and then you have an atom whose primary key contains only constants of free variables. So this works. So you have rewritten the atom that was not attacked, which exists because the attack graph is acyclic. And then you have a new query where this first atom is removed. And now I claim that you can do the same procedure, that in the remainder query, there will be an atom that's unattacked. You do the same rewriting. Now, it's not so clear that by removing the atom, the attack graph will change. And maybe you could say, couldn't there be a cycle that pops up? No, we show that this is impossible. So now you have a recursive rewriting. And actually, rewriting, you rewrite one atom at a time, actually in the order of a topological sort of the attack graph. That's basically the rewriting. So if the attack graph is acyclic, you can have a topological sort of your atom, and you rewrite it like exists for all in the order of a topological sort. And this works. Yeah? Yeah.
This was the example where you added W, and when you did not have W, you had a W.
Yeah. But it, yeah, but okay. But if I rewrite this atom, X becomes a free variable. I understand. So in this original query, X is not free, right? And there's a cycle. Now, once I've rewritten this atom, for the computation of the remainder of the attack graph, I have to consider that X has become a constant, right? And then you will see that the attack graph, yeah, good remark, yeah. So I took care of this in the proof, yeah. It's where it's understood that the variables of the atoms you are rewriting are treated as constants. Yeah, good point. Yeah. So this is actually the proof. Like, assume that the attack graph is acyclic. There must be an atom that's unattacked. Therefore, it's verifiable. And we know how to rewrite this atom, and you do this recursively, and you have a first order rewriting, right?
It's important to say that the size now is clear that the polynomial is the size of the graph.
Yeah.
Therefore, polynomial is better. So there is no way on this query to be correct. So it's always small, right?
Okay, yeah.
the size of the rewriting is actually linear in the size of the original query. Yeah, good point. Yeah. And actually, we show that the converse is also true, that if the attack graph is cyclic, then Q has no consistent first order rewriting. And intuitively, what this means is every atom is attacked. You cannot reify any of the primary keys, and it means that there's no first order rewriting. So intuitively, this means that the only rewriting you can produce is by this reification trick. But this is not a proof, of course. This is just like an intuition. So now we know what happens if the attack graph has is acyclic. What about cycles? Now, we have this query where there's obviously, there must be a cycle because otherwise we know that it's going to be complete, so it cannot be an F4. And you see here, P attacks N, the variable Z, because P plus is just the X, and N plus is just Y. And so they attack each other. So it's cyclic. And we showed that it's going to be complete. Now there's another result that was proved like I think 2010 in a paper that if you have this X, Y, Y, X, then you can prove that's in polynomial time, but not in first order. And it's not in first order because also here you have an attack side. R attacks S using Y and S attacks R using X. So the attack graph is cyclic, but still certainty Q is in P. And then you can wonder what's going on here. Can we distinguish these cases? And you see what's happening here is something like, okay, you are using here a join on a variable that's not in the key. Whereas here it's like, okay, you are using Y to join with this primary key. And if you, from this intuition, I would say, okay, let's define weak attacks. We will have weak attacks and strong attacks. And we say that an attack will be weak if I take all the functional dependencies, then R, the key of R functionally determines the key of S. So here it's this attack between, for example, P to N is not weak, so it's strong because yeah, because X does not determine Y, right? You have functional dependence, X determines Z and Y determines Z. So X does not determine Y, but here I have like X determines Y. And on the other hand, Y determines X. So in this case, this attack cycle is weak. So this was like in the beginning, it was just like an intuition, and it seems to be the right intuition. Of course, this is not a proof, but finally, the result we proved was then the following, like, let Q be a self-join-free Boolean conjunctive query. If the attack graph is acyclic, then certainty Q is in FO. I gave you an intuition of the proof, and I hope you are convinced and happy with that intuition. Now, if the attack graph of Q has a cycle, but there's no cycle with a strong attack in it, then certainty Q is actually log space complete. And in all other cases, so if you have a cyclic attack graph where there's a strong attack in it, then the query is going to be complete, right? So this is I think this is a nice result, which for the case of primary keys completely covers all cases, right? Actually, this L completeless here, it's also, you can also have a descriptive complexity result. Actually, it's just proven by expressing it in a symmetric stratified data log. So there's a logic where you can express these queries, right? So, and I think this is a much nicer result than just saying like, okay, for primary keys, it's going to be complete because, well, it's only going to be complete in this case. And it turns out, actually, if you look at real queries, like often what's happening in joins is something like this, having weak attacks where you join on a variable, but the variable is a foreign key primary key join. And if you do that, then the attack will be weak. So I still believe that for many real life queries, they can be written in first order, right? And this query, of course, I think it's not a natural query because you join on a non-key attribute. So again, this, of course, as a corollary, we have like the dichotomy result. So for every self-join-free Boolean conjunctive query, yeah, here I took the complement to make it clear that's NP or NP complete. And again, remember the point of dichotomy theories. It means that for every self-join-free Boolean conjunctive query, we can take this problem and tell you whether it's NP complete or NP, and we know that it will never be NP intermediate. Right? Now, we still have self-join-free. So, of course, the question is, what happens if we drop self-join-free? And I know in Bordeaux, there's some people working on this. What happens if you do that? This is a conjecture, like, and I invite all of you to work on this conjecture because I do not want to retire before knowing the answer to this conjecture. Like for every Boolean conjunctive query Q, certainty Q is either NP or co-NP complete. So we want to live this result to conjunctive queries that can have self-joins, right? That's the point. And it turns out that all this machinery of attack graphs, it fails completely when you have self-joins. And then you can go one step further and say, what about unions of conjunctive queries? And unions of conjunctive queries, they have been introduced this morning. It's like, in this case, if you have conjunctive queries, it's just a disjunction of Boolean queries, right? And you want to lift this conjecture, even conjectures for every Boolean union of conjunctive query. This problem is either NP or co-NP complete. And then there was a nice result by Gaëlle Fontaine. You know, the title is, Why is it hard to obtain such dichotomies? And she actually showed that if you can find such a dichotomy for a union of conjunctive queries with self-joins, then such a dichotomy would imply Bulatov's dichotomy theorem for conservative CSP. It's a deep result in about CSPs. And if you look at the, well, I don't understand the proof because it goes to algebras and so on and so forth. So there's little hope that, well, so it would be a stronger result, this dichotomy, than this existing result of Bulatov, which maybe there's still hope that you can go the other way around, that you can take this strong result and show that this implies the dichotomy for conjunctive query answering, but, right? So for union of conjunctive queries, it will be difficult. I think I will retire before that's, but I still hope that someone can come up with this conjecture, right? I still have only, so I will not, yeah, in a recent paper, I told you that this is only primary keys, and you can say, oh, this is very limited, it's only primary keys. So the next thing to do would be like, why not add primary keys and foreign keys? If you know how to do primary keys and foreign keys, then, I mean, these are the most important constraints in relational databases. We had a paper at POTS this year where we do add foreign keys, but only in a restricted setting. I will not go into details. You can look at the proofs, but for example, if we add foreign keys, then things become tricky already. I don't want. Okay, then there's the counting problem. That's another problem, like, and that's to make it's very similar to what we have seen this morning about probabilistic databases. So now we are asking whether a query is true in every repair. But assume that the query is true in 99% of the repairs, then you would like to have that information. And currently you would say, no, it's not, the answer is not consistent. It's only true in 99.9% of the repairs. So why not try to count the number of repairs that satisfy a query? that would be, that we come close to probabilistic database. I give you a Boolean query, a database, and you tell me the number of repairs where the query is true. And the number, it can be expressed as a fraction, because if we have seen the number of repairs is just the product of the cardinality of the blocks, right? So that's another task. So sharp certainty queue, you take a database, you know, how many, and then again, you have a complexity classification task. Okay, so the input is a query, and you determine lower and upper complexity bounds on the complexity of this problem. Here in terms of FP is just function problems that can be solved in polynomial time, because it's no longer a decision problem, and sharp P. And actually, there is also a dichotomy, and recently this was nicely generalized for functional dependencies by a paper by Andreas and co-authors. Very nice result. And so, and also to link to Antoine's talk, actually here we are very close to block independent disjoint probabilistic databases, right? Because if you are counting the number of repairs and you know that you have to pick one tuple of each block, and you say, what's the probability of taking that tuple? Well, you can just suppose a uniform probability distribution in your block. If you have 3 tuples, they have 1/3, 1/3, 1/3. So you have block independent disjoint probabilistic databases where within the block you have the same probabilities, right? And this is a special case of block independent disjoint databases we have seen this morning, where actually these probabilities can be just any numbers, right? And there is a difference though, because you could think that here this result we had just follows from existing results in probabilistic database. The point is that if you have a block in our database, you must really pick one tuple from every block. Whereas in this kind of databases, there might be a block where the probabilities don't sum up to 1, and so you can pick no tuple from a block. That's a technical difference, right? I think in this database they all sum up to 1, right? What I like about this is, like, you know, in inconsistent query answering, people say, oh, inconsistency, it looks like a bad thing, it's inconsistent. And that's why I also preferred at some point to use certain query answering, because certain looks, it sounds better, right? But here, like in probabilistic databases, they use this inconsistency just to model probabilities and to have nice results. So for me, inconsistency is not only a burden, but it's also a chance. It allows you to model things that you would not be able to model otherwise, right? Okay. Okay, I think. Okay, I'm at the end, right? Yeah, I come. So this talk was definitely very much biased towards my own interests. So I apologize for all people who have obtained very nice results in this field and that were not mentioned. You can have a look at the paper I wrote for the database principles column, and there are many other topics that are very relevant and very interesting. Data exchange and database repairing, approximations, preferences. Benny has a lot of nice work about this. Implementations, database management systems, queries with negation. Up to now, all queries were like conjunctive queries, and this is fine because we have this monotone behavior. What happens if you add negation? Description logics, I think tomorrow people will have to, and Carsten also, and Diego will have to tell more about this problem, like what happens in description logic, graph databases, and so on and so forth. So, okay, this terminates my talk. Thank you.